So we're going to look at the electric field from a line of charge, and this will be a finite line of charge that has some length L, and we're going to look at what is the magnitude and direction of the electric field at some point A, which will be in the middle of the line of charge, but at some distance r away from it. And to answer this question, we need to know two equations. We need to know that the charge density lambda is equal to Q over L, and that the electric field for a point charge is 1 over 4 pi epsilon naught times the charge divided by some distance d squared, where this distance is, for the point charge, is the radius. Now, to set this up, we're going to basically just set our line of charge up on an xy axis. So let's have the middle of the line of charge be at y equals 0. So the top of the line of charge will be at y equals L over 2, and the bottom will be at y equals negative L over 2. And this puts our point right on the x-axis. And we're going to look at the electric field from the top half. And at the farthest point away from the point A, our electric field, so this is at L over 2, has some distance d, and gives us an electric field, and we'll say electric field subscript U, just show that this is from the upper half of the bar. And this has two components. It has a y component and an x component. And the angle between them is theta. And we can do the same thing for the lower half. We have some distance d, that giving us an electric field E, we'll say EL from the lower half, and this gives us two components, a y component and an x component. And the angle is the same because the point is in the middle of the line of charge. And to find the magnitude and direction, we just sum the components together. So let's look at the y components first. The lower half of the charge's y component is equivalent to the upper half y component, but opposite in direction. So they cancel out. And the x component from the upper half is equivalent to the x component in the lower half, and they are equal in magnitude and direction. So we can actually just add them together, and because they're equivalent, we only have to solve for 1/2 of the line of charge and then just multiply it by 2. So our total electric field is going to be equivalent to 2 times the electric field and the x component, and that's, again, just evaluated either using the upper half or lower half. And the electric field is changing based off this distance d, and this distance is changing as we run along the line of charge. So as we take small snippets of this electric field, so small little dLs for the length, and since we put it on the y-axis, this dl is little dy's. So small little sections to figure out this electric field, we're going to sum all of those together. So we're going to take little tiny electric fields at each of those points and sum them together. And so we don't have to calculate a whole bunch of little individual ones individually. We're going to use integration. So that's, we're going to apply that there. And the changing component, like I said, is going to be this distance here and the charge. And we can apply that using our charge density equation. So lambda now equals dq over dl, and we just said that dl is also equivalent to dy since we set it up on the y-axis, so it's equal to dq over dy. So that's how our electric field is changing. We're also looking at just the x component of the electric field, so just this component of the electric field, and the x component is the cosine component because cosine is adjacent over hypotenuse. And our adjacent is our EX, and our hypotenuse is our E. So in order to find EX, we just multiply cosine to E. So EX equals E cosine theta. So our dE total is equal to 2. We can bring that 2 out because it's just a constant. dEx, which is equal to 2 dE cosine theta, which is equal to 2 times 1 over 4 pi epsilon naught. And so these are all constants. We just set the changing element of our electric field is this dq dy. And we can rearrange this equation, so instead of saying dq, we can say lambda dy. Lambda dy. And then we gotta not forget our 1 over d squared. 1 over d squared, and our cosine theta. We can continue to simplify this equation by breaking down our d and our cosine. So if we take a look at what our cosine is, right, so cosine theta, if this angle is theta, then this angle is also theta. And we can write, since we know our cosine is adjacent over hypotenuse, we can write that as our adjacent, we've labeled as r, over our hypotenuse, which is d, so that we can substitute that in for our cosine. So our d e total is equal to 1 over 4 pi epsilon naught. I'm not simplifying those yet. You'll see why later. We can bring that lambda up top because it's also constant. Lambda, we have 1 over d squared, and then we have, instead of writing cosine, we have r over d, and that is dy. And so we can write d e total as equaling 2 lambda over 4 pi epsilon naught, 1 over d cubed r dy, and this r is also going to be a constant, so we can also just write it right here. These are all our constant terms, which we can just take out. We don't have to integrate. But now we want to get this d in terms of y, right? So we need to find another way to represent it. And to do this, we're going to use Pythagorean's theorem. We know that d is the hypotenuse, and we know that the hypotenuse is equal to the square root of the sides squared. So the first side is r, so r squared, plus, and then this is our y. This is our y side, so y squared. So that is what our d is. And if we do d cubed, so d cubed is the same as saying r squared plus y squared to the 3 over 2. Because we're cubing that. Basically taking a square root times a square root times a square root. And so our d e total becomes 2 lambda r over 4 pi epsilon naught. And this is 1 over r squared plus y squared to the 3 over 2 dy. Now it's in terms of something we can integrate. And actually, in order to solve this, we're going to integrate both sides. And the right side, or the left side's easy. It just integrates to e, right? Didn't mean to erase that too. This side will integrate. Right, so there should be an equal sign there. I ran out of space, but don't worry about that. We're going to integrate this in terms of dy. And we're integrating from 0 to L over 2, because that's half the length of the bar. Because we're just looking at the upper half, L over 2. So this integral is pretty commonly done. There's a few steps to it, but we're actually going to do that together. We're going to solve, I'll walk you through how to solve this integral. And we're going to figure out what the electric field is integrated over these values. All right, so when we integrate this, we're basically just setting it up to say our total electric field, right, is going to be equivalent to, we can pull all our constants out, 2 lambda r over 4 pi epsilon naught, and that's being evaluated from 0 to L over 2 of 1 over r squared plus y squared to the 3 halves dy. And to solve this integral, we are going to substitute for y. So we're going to do it via substitution. So we're going to substitute for y to be r tangent u. And so this, if we were to rearrange this equation to solve for u, this would give us u equals y over, arctan first. So the arctan of y over r. And if we were to do the derivative, so dy equals r secant squared u, because the derivative of tangent is secant, and that would be du. So having all three of these, now I can apply them into my integral for substitution. So the integral becomes 1 over r squared plus, instead of writing y, I'm going to write r squared tangent squared u. Right, that's all the 3 halves. Instead of writing dy, I'm going to write r secant squared u du. So now everything is in terms of u. And I can use a little fancy footwork here. I can pull that r out, and the r is actually constant. So this becomes r over, this becomes r cubed, and that gives me 1 over 1 plus tangent squared u to the 3 over 2. And I can write, just simplify my space here, this is secant squared u, and if you already see the trig identity, then good for you. This is du. A trig identity, secant squared, is equal to 1 plus tangent squared, so I'm going to rewrite that in. So that gives me, and then this simplifies to 1 over r squared. This becomes 1 over this is secant squared u to the 3 over 2. Oh, we gotta make sure we keep that secant squared on the top. U du. This simplifies out 1 over r squared to the 1 over secant u du. And secant is the same as saying cosine, 1 over cosine. So we can write this as 1 over r squared, the integral of cosine u du, which is 1 over r squared sine u. And then we have to undo the substitution. I'm running a little bit out of room. And then, again, not forget, we are also applying the parameters and the constants. We'll get there. This is 1 over r squared. The sine, now this sine is going to look a little tricky, but it's not too bad. So we're going to do the u substitution for this one. So it's the sine of the arc tangent of y over r. So to evaluate the sine of the arc tangent of y over r, we just have to not overthink it. We have to look at what is this really saying. It's saying I have some triangle where if I have this angle, the arc tangent is the opposite over adjacent, right? So it's this opposite angle, or opposite side y over some adjacent r. So what is the sine of this? This sine, and we'll call this the hypotenuse, right? Which, using Pythagorean's theorem, we know is the square root of the sum of the sides. So that's y squared plus r squared. So the sine of this same triangle, is simply y over this y squared plus r squared. So that's all I'm putting in here for that. So I can say then this is now equal to 1 over r squared y over the square root of y squared plus r squared. Now I just apply the constants and the range that I was evaluating this at. So let's apply that. So I'm saying my electric field total is equal to 2 pi r over 4 pi epsilon naught multiplied by this evaluated from 0 to L over 2. Right? So, and I can pull the r's out because this is a constant. So this then simplifies to 2 lambda over 4 pi epsilon naught r. And I get that being multiplied to y over the square root of y squared plus r squared, evaluated from 0 to L over 2. And now I just plug in the L over 2 and the 0. The 0 is just going to cancel out, so I get my E total is equal to 2 pi over 4, or 2 lambda, sorry, over 4 pi epsilon naught r. And that is going to be equivalent to L over 2 over the square root of L squared over 2 squared is 4. It's getting a little small here, sorry. Plus r squared. And then again, like I said, the 0 will end up just canceling. The reason why I didn't simplify this 2 and this 4 is this 2 will cancel with this 2. So what I am left with is my total electric field is equal to lambda over 4 pi epsilon naught times r, which is the distance away from the line of charge, times the length of the line of charge over the square root of the length squared divided by 4 plus the radius squared. And this is the electric field for a finite line of charge.